going to start talking about linear system of equations. So that's the first thing that we're going to talk about. So linear systems of equations. Linear system of equations. And linear system of equations, if you guys remember correctly, those are those who are given in this form. They're given in the form A, which is a square matrix, X, which is the solution vector, and B, which is the right vector, the right hand side vector. So this is the traditional form of our linear system of equations. We have our AX equals to B. The way that we're familiar of solving this, so if I wanted to solve the familiar way that you have seen in pre-calc and you have seen in your previous classes, if I wanted to solve for X, what I do is I do the inverse of A multiplied times B. And one thing that you have to be careful, and it's not that you have to be careful, but when you're solving for A, when you're solving for your X vector, the reality is you're not dividing by A, and you're bringing it up, and that's why it's negative. Linear algebra is different than algebra in the sense that we're treating vectors and we're treating matrices. Vectors and matrices, you cannot treat them like just normal constant or scalars, how you do in traditional algebra. Like what you're doing here is you're left multiplying both sides by A inverse. So that's how you get like the identity matrix and all of that. And we just omit it because it makes no sense to use it. You're technically, yeah, exactly. So you're technically multiplying both sides by A negative 1. By the A inverse of the matrix A. So where you're not moving around and dividing, that's a misconception. But two things that you want to keep in mind. So what I will say, remember, I don't know how to type anymore, so give me 1 second. Or write. I've been doing too much typing lately. So remember, if you want to find your residual vector, it's going to be AX minus B. And I can continue using the notation. Another notation that Dr. Kasab likes to use is he puts like a little squiggly guy at the bottom to indicate that it's a vector. And then under the matrix, he puts just an underscore. So that's another way of looking at it. But residual is AX minus B. Or you can say that your residual, it's equal to B plus AX. So if you have AX times B, if you take this guy and you move it to the other side, you're going to have B minus AX. These two guys are the exact same thing. It's just the way how you take this equation and you set it equal to 0. I believe so. I believe that the comment you're saying is right. Right now my brain is, I need to move this out of the way. So I'm going to close the chat. So if you guys need to say anything, just let me know. Just say, somebody speak if you see that somebody's trying to say something on the chat. But yeah, so this equation, you have to keep it in the back of your head. You have to know how to do residual vector. You have to absolutely know how to find the residual vector for linear system of equations. Now, be careful, because I'm going to say this right now, and I will reiterate once we get to that point. But this is how you find residual for linear system of equations. This is only for matrices. I'm going to delete this, but if we're doing nonlinear Newton-Raphson, so if I have nonlinear Newton-Raphson and I want to find the residual vector for nonlinear Newton-Raphson is the vector of the absolute value of the evaluation of the vector. So it's the same thing that you saw before. It's the exact same thing that you saw before, where we have a nonlinear Newton-Raphson. If you wanted to evaluate the residual at a certain x, you will plug it into the function, take the absolute value of that. The difference here is that this x is a vector, and we're plugging a vector inside of the vector function. So my function is a vector, and then if I take the absolute value of that, I will obtain a vector. So the final product, that's why it's called a residual vector. Our residual is no longer only one value, which is the reason why we do the infinity norm, because we want it to be one value. We don't want it to just be a vector, because the vector has a bunch of components. It's not really telling me anything intuitively. So make sure you know how to that if you're given a linear system of equation in this form, if you're given a matrices, this is how you find the residual. And then if you want to find the iterative convergence, which is the epsilon. I'm gonna start using the notation that he uses. I'm tired of writing those guys. That will be the absolute value between the k at the +1 iteration, or you can call it k, and then the iteration at the one before. So when we put things inside of parentheses like this, we're talking about an iteration. That's not a power. So if I say something like, oh, you have x0, this means the initial guess, or at the 0 iteration. If I do 1 or if I do 2, that's talking about iteration. It's not to be confused with something like that. That's x squared. So if it's inside of a parentheses, it's often referred to by mathematical terms as that's the iteration. So these two things you have to keep in mind. You have to know about this. Again, this guy is a vector, this guy is a vector. The subtraction or addition between two vectors will give you a vector. So the epsilon is a vector, and residual is also a vector, which brings us to the point of, okay, if we have a vector, then how do we find the norm for those vectors? Because this is very important, and that you understand it intuitively. I know some of you, this might be redundant because you already know it. But the whole idea of us finding norms is because if you have a residual vector, the residual vector is not telling me anything. Like, there was something when we were doing linear Newton-Raphson, I knew that as I kept finding more and more iterations, as I kept iterating through my values, and I kept converging to a solution. Let's say that solution was like 0.02. I know that my residual in this case was only one value. I know that as I kept going through my residual, as I kept going 1, 2, 3, like however many I did, I know that this residual will go to 0. And same thing will be for the epsilon. But the problem is here, when I was doing linear Newton-Raphson, my residual was only one value. So it was very easy. I just have to calculate the residual at every single iteration and just see if that value was indeed going to 0. For nonlinear Newton-Raphson, in any sort of system of equations, it's more tricky because every time we're evaluating a residual, and this guy is a vector. For nonlinear Newton-Raphson, every time we find a residual, it's a residual vector. So you cannot just tell me, oh yeah, that residual is going to 0, because it's like, okay, what do you mean that residual is going to 0? Are all of the components of the residual going to 0? Which is not always the case, because they converge at like different, or they like fluctuate at different values, each of those components. So it's like, if you tell me, oh yeah, the residual is going to 0, I cannot just see it intuitively how you're telling me that all the values of this vector could be a vector of 1,000 components. I cannot just sit there and look at at each of the components of the vector, however many components there are, and be like, oh yeah, it looks like they're going to 0. It makes sense. Like, it's a waste of time. So, which is the reason why we use norms. So the idea of norms is, if I use something like the L infinity, if I apply L infinity to this residual norm, which I'm gonna say is at the end iteration, what this is doing is, hey, like if I wanted to say, hey, give me the biggest value, give me the largest value. So I can say, give me the largest value, but I also want it to be absolute, which means I don't care if it's positive or negative. I just want you to go through this vector, to go through all of the components of that residual vector, and I just want you to give me what the largest magnitude, the component with the largest magnitude is. Because what happens is, if I have this vector, if the largest component of that vector, like if that vector has 5 components, if it has like, oh, 1, 2, 3, 4, and 5, assuming this is my residual vector, when I do the L infinity of that R, I will get 5, because that is the 5, if that's the largest component. If all of these guys are going to 0, like if all of those components, all of these guys were going to 0, this guy, the 5, whichever is like the largest components of all times, that will tell me that the whole vector is going to 0. If the largest component is going to 0, all of the other components are going to 0. It's just kind of like I hope that you can understand that sentence as kind of like as I'm delivering it. If the largest component is going to 0, Therefore, all of them are going to 0 because that I just said that that's the largest component. So that's why L infinity, L2, L1, whatever you want to use, whatever norm you want to use, that it's just intuitive. Now, you might be asking, why do we have so many norms? Like, why do we have L1? Why does Kasab want us to do L2 on the project? And then on the exam, we do L infinity. And then it's so you can see it's a different perspective. It's different applications. So, for example, the L2, L sub 2, it's known as the Euclidean norm. And it has to do, for example, with the when you do a statistical analysis and you do like, oh, the square root of the square of the sum of the errors or something like that. Like, that's exactly where it comes from. It's a calculation of a magnitude based on the summation of squares. And that you can think of it as the Pythagorean Theorem, which is something that I explained in one of the labs. You can think of it as that way. Like, I want you to give me the magnitude of a vector, and a 3-dimensional or a 2-dimensional vector is a 2-dimensional vector, particularly. It's very easy to see because we're used to dealing with those type of dimensions. We're used to comprehend up to a third dimension. But once you go into mathematical analysis, when you have n dimensions and all of this stuff going on, your tools have to be more powerful. So that's the whole idea of numerical methods. We're teaching you guys a bunch of shit that seems useless, and it seems to be that like we're redundant. We just keep repeating the same thing over and over. But the reality is, it's just a tool for the job. You have to use the right wrench if you're trying to get the spark plugs out of your car. Otherwise, you're gonna strip the freaking bolt, and you're gonna have to call someone, and they're gonna just look at you like you're a pile of shit because you just didn't do it correctly. So that's just not to go on a tangent. That's a little bit of the background. But a problem that they can give you is, so for example, let me say an example. Something that you can have is if they say, okay, you're given the form, and this is how they tell you what type of approach you have to follow. So they will say, oh, you're given the form AX. That's not right. Sorry. AX equals to B. When they tell you something like this, you know it's a linear system of equations. You know that all the equations that I showed you before, they apply. So when they give you a linear system of equations, they will usually tell you, hey, this is a linear system of equations given in this form. So that's how you know which residual formula, which the iterative convergence formula you have to use, or equation. I'm sorry, not formula. But they will give you so they're saying given the form and given A and B, so they will give you A and B, which is all good and everything. They will say, for example, like, okay, we found that the inverse, which that shows you how useless this is, but the inverse of A is given as, so they will provide you your A, which is going to have a bunch of values. Let's say this guy is a 3x3. And then they will tell you A inverse. And they will say, okay, A inverse is also a 3x3 because it's the inverse of that guy. And that one is also a 3x3. But then they're gonna give you the value of A inverse, and they're gonna give you the value of your normal A. And they will say, answer the following questions based on this. They will also give you B, by the way. So don't freak out.
So you're saying in this kind of sense we can almost disregard A because we would just have to determine A.
Well, it depends on the kind of question that they're going to ask you, because remember, this type of problems, the way that Dr. Kasab likes to do it, it's like, hey, you're given this information, now go and answer the next 5 questions, the next 10 questions, which can be good or can be bad, because you don't know what information is relevant until you run into the problem that asks for it. So the first question that is going to ask you, it's going to say, so the one of the questions that you have to know how to do is, they will say using the infinity norm. So using L infinity, that's like one of the first questions. Using the L infinity, you have the L infinity of, oh my god, this thing printed like shit. I really sorry. So using L infinity, and you also have your A vector, Yeah, so this is how you write it. So if I wanted to say using the norm, this absolute value, this double bar usually means the norm of something. So I'm using the infinity norm of the matrix A and the infinity norm of the matrix negative A, and then they say, okay, what is and this is something that you probably know, what is the conditioning number? So that this is a question that will be on the exam. You have to absolutely know it. Now, you may be wondering, okay, so how do I find the conditioning number of a value? And that's why this is very important. So they're saying, okay, you have used the infinity norm, find the infinity norm of your normal matrix. Again, you're given your matrix A, so you have to find the infinity norm of your matrix A, and you're given the inverse of A. So you have to find the norm of your inverse, of the inverse, the infinity norm of the inverse. And what you do at the end, if I remember correctly, because again, I'm a slacking piece of shit and I never review before I do a review, just because that's the way I am. If I remember correctly, the only thing you have to do is multiply the result of this two. Because remember, infinity norm, it's a value. Infinity norm is a value. It's just a normal scalar. So you obtain a number from this, and you obtain a number from this, and you just have to multiply those two. If I remember correctly, I think that's what it is. I can double check towards the end, but again, I don't want to waste too much time just working on examples, and then we don't get through the whole exam. But
no, you're correct for the conditioning number.
Okay, perfect. Thank you. That's reassuring. That means I'm not full of shit. But make sure you know how to do and I'm not going to repeat it because I taught this in my lab when we were at either lab or office hours before. So I know a lot of you guys are from my lab or my office hours. And the infinity norm for a matrix is different than the infinity norm of a vector. A vector is you just look at them, and you make all of the values absolute value. All of the values, you make them absolute values, and you pick the highest value in magnitude, and that's for a vector. For a matrix, I think you do like column summation or something like that. Like you grab them one by one column, and you like add them and take the absolute value, or like you take the absolute value and you add them, like you turn it into a vector, and then you do the normal L infinity. So just make sure you go over that. Make sure you know how to find the L infinity of a matrix, because you guys have been doing a lot of L infinity or finding norms for vectors. You guys don't really find norms for matrices, so make sure you definitely know how to do that. Also know what the conditioning number represents. So do you guys know what the conditioning number represents in a matrix? Like anybody that is brave enough, like, oh, if you have that you can represent if the system of equation is well conditioned or if it's ill conditioned, and what kind of residual you can expect. Can you expect a small residual? Can you expect big residuals, or an accurate or inaccurate solution? So that is question 2 on the exam. So make sure you know what conditioning number is, what the conditioning number represents. Not only how to calculate it, but also how to find what the conditioning number represents. What does it have to do with the residuals? What does it have to do with the system being either well conditioned or ill conditioned? I guess another thing that we should talk about, since we're already talking about this, is how to find the conditioning number and what conditioning number represents for a system. Like, what does it represent with respect to residual? What does it represent with a system being well conditioned or ill conditioned? And then another thing to talk about is pivoting. So pivoting, for the exam, you don't have to implement this, so maybe do not focus too much on how to do it by hand, but primarily on like what represents. So if you guys remember from project, I believe it was project 3, I think, that we did pivoting. The whole idea that we did pivoting is to guarantee convergence, and in practice it's a good idea to implement pivoting. However, we don't need to do pivoting if our matrix is what? Can you guys recall? There is
diagonally dominant?
exactly. So if it's that, if the matrix is diagonally dominant, we don't have to implement pivoting. If it's not diagonally dominant, we implement pivoting because we want to turn our matrix into a diagonally dominant matrix, so we can guarantee convergence. So just make sure you're aware of that. That if pivoting, you don't really have to do it by hand, because it's just a procedure. It's just a procedure to turn it into diagonally dominant. So they're not gonna ask you, hey, here's this matrix that is given, turn it into a diagonally dominant matrix. No, it's more of like, hey, like, is this matrix? Do you have to implement pivoting? Yes, no, and why? Why will you have to, or why you don't have to? Another thing that it's very important that you know is how to do Gauss elimination. And Gauss elimination, which it's a little bit annoying. It takes some time. I know some of you have mentioned before that you can do it by the calculator. You can use a calculator. The only calculators that I'm familiar with are the TI-36X Pro, just because TI is a piece of shit of a company and they like to oversell you products by the big. But I know a lot of calculators are able to do it. If you're using something like the 30X, I think you hate yourself. But if you're using the TI-36X Pro, I think this one is able to do it. And if you're using a TI-84, a TI... Okay, so if you're using a TI Inspired, there's something wrong with you, because at that point, buy a computer. But if you have a TI-36X Pro or a TI-89 or something like that, you have an overpriced piece of technology, just like Apple, but you can use it. You can use it, and I know there is a way of doing Gauss elimination. And the reason I'm like saying all of this crap is because you have to know how to do triangulation. So you have to know how to triangulate, because they will ask you, and this is upper. So you have to find the matrix that is in upper triangular form. When you're doing Gauss elimination and you have your matrix and you put it in upper triangular form, because you're gonna do like back substitution, and all of these guys is filled with a bunch of zeros, and you have all your coefficients at the top, they will ask you something like, hey, can you give me the coefficient like 2, 1? Or can you give me the coefficient like 3, 3, for example? Something like that, like the last coefficient. Then they can ask you anything like that. So you have to know how to solve using Gauss elimination, but very importantly, you have to know how to do the upper triangulation, and you have to know how to do it correctly. So know how to triangulate for the process of Gauss elimination. Not only just, I'm just gonna put it on the calculator and it's gonna give me the answer, because then you're gonna miss you're gonna miss more than one question, because they're gonna ask you for a component, so an n by n, or n, not n by n, because that means it's the same number, something like n by m, or they can ask you for a specific value of your upper triangular. So they will ask you for a value of your upper triangular A matrix and your triangulated B vector. Because remember, when you're doing this process, you're triangulating both of them at the same time. Because everything that happens on one side of the equal sign affects the other side of the equal sign because of equality. So make sure you absolutely know how to do that. And it's a Gauss elimination without pivoting, by the way. So you're not implementing pivoting. It's just traditional plain Gauss elimination. Nothing out of the ordinary.
Will we need to reduce/simplify, like bring it down to pretty much like one diagonal, or just put it in upper?
No, yeah, exactly. Just put it in upper. You don't have to put it in reduced row form or whatever it's called. You don't have to do that. You just have to just upper triangular, and that's it. You have to carry out. So the question says carry out the Gauss elimination without pivoting. And then they say, upon the triangulation, give me such element, give me such element, and give me such element of the triangulated vector and the triangulated matrix. So, and then they say, like, they can ask you for the triangulated upper for any element of your A triangulated, any element of your B triangulated, or any element of your solution vector. So after triangulation, your solution vector, and your solution vector, this is something that you could like easily find just doing A inverse times B. So if you don't know how to do this one and know how to do this one, because you were slacking, you didn't study how to do Gauss elimination, you don't know how to do triangulation, or you forgot, or you have no idea how to do it and you're running out of time. Remember, you can the solution vector doesn't change with triangulation. It's just triangulation is a technique to find it, and so then we can do back substitution. But if you don't know how to do triangulation, if you need to find the solution vector, so at least you get one of the questions, just A inverse times B. Don't freak out, just do what you know how to do, and that's it. So for Gauss elimination, again, Gauss elimination is a linear system of equation. So when I say, every time I'm gonna say it's a linear system of equation, or I'm specifying what it is because these two guys, you're gonna have to calculate them. So you're gonna do Gauss elimination, and you're gonna have to calculate the residual, and you're gonna have to calculate the residual vector and the E. And remember that L infinity, or the norm, is a thing. So every time we ask you to calculate a residual, every time we ask you to calculate any information like that, every time we ask you, hey, find the residual vector, find the iterative vector, the iterative convergence vector, most of the time we're going to ask you to do the infinity, the L infinity, or the Euclidean norm. We will ask you to do a form of norm. The two most popular ones, at least for the purpose of this class, is L2 or L infinity, and both of those you should be able to know how to do them. So another thing that is very important that you understand is one thing that they can also ask you for this, and this is, I'm going to put it on a start because this is kind of like maybe not of the traditional process that you will do, how you will go about this problem particularly, but the number of floating point operations. Can you calculate the number of floating So can you calculate the number of floating point operations? And of course I made a mistake.
That'd be like the kn squared.
Yeah, so it's that thing that if you know, what is it? Like if you know the size of the matrix in one direction, the size of the matrix in the other direction, and then the number of iterations that took you, if you multiply those two, you get the floating. It's like it's like FPO. I think that's how they call it, FPO. And so usually you have to be careful by, I guess it's not relevant for this class per se, but I don't know. I've taken a lot of math classes, so that's why I when I look at something like this, you see that I write n and m, so I'm not assuming that they're the same dimensions. Usually you have a square matrix, so you have an n by n, which means if it's a 2 by 2, it's a 3 by 3, it's a 4 by 4, 5 by 5, n by n. And usually, like, somebody in the class will always say, oh, you know, that formula, you just have to do the n squared times the k, and that will give you your number of floating point operation. And it's like, no, you're full of shit. It just so happens to be a very specific case where you have a square matrix. And so yeah, you have an n by n in this case, but I type it like this. You can think of it if you want as, hey, just take the easiest thing you can think of. Floating point operations of a system of linear equations of a matrix is the dimension on one side, the dimension on the other side, multiplied by the number of iterations that it took me to converge to a solution. So if it takes you 10 iterations to converge to a solution, it's going to be this number of rows, the number of columns, and then the number of iterations that it took you to converge. That will give you your number of floating point iterations. By Gauss Elimination. This is a very interesting question, because the number of, so that this formula, the one I'm talking about, I think it only applies for Gauss Seidel. I don't think it applies for Gauss elimination, because Gauss elimination is not an iterative process. Gauss elimination is an exact solution, so you can. Yeah. So that's what I mean. Jacobian and Gauss Seidel, it applies for iterative methods. So make sure you know how to find number of floating point iterations for for direct methods. Because this, if I remember correctly, this one right here, the one that I just wrote, this is for indirect methods. Or iterative methods, I should say. So this is for approximative methods, for Jacobian, Gauss Seidel, and things like that, because that's where the K factor comes into play. I'm trying to think, maybe, let me see.
Isn't it M cubed for Gauss elimination?
That's what I'm trying to think if it's that, but I don't want to give you a solution that could be wrong. Gauss elimination by pivoting, Gauss elimination, because the dimensions of the matrix is a 3 by 3, and I don't see anything that is 36, or I'm sorry, 3 by 3 is 9. I don't see a 9, so I don't think that's what it is. It's a very specific solution. It's a very specific equation, but I'm not sure what it is at this time. I remember exactly for indirect methods, so make sure you search for this. It's very important because it's on the exam. You know how to calculate the number of floating point iterations for direct methods, for linear system of equations. You always have to specify what kind of realm you're working in or you're working on. So given the coefficient, blah 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 blah, can one find it? Another thing that this one will be like, I think this will be like the last solution of direct methods. But if I give you, if I give you a system, so if I give you a system where I am specifying my A, I'm specifying my X, and I'm specifying, so wait, what is this? Give me 1 second. Given the following, it just cracks me out. There is a type on this. So given the following matrix something, and then that is called this, that is called A, and then the matrix is called something completely different. So if I give you a system in this form, so this is the form, and I provide you. So I provide you with A. So A is the only thing that I'm giving you. I provide you with A. Can you find A inverse, and can you tell me if you can solve the problem? So you can tell me if A has an inverse, and you can also tell me if the problem, the linear system, can be solved based on just the information provided by A. So there are multiple ways of doing this. How can I know if a system can be solved? You can find the determinant of A. Is the determinant of A equal to 0? If it is, then of course the problem cannot be solved. And that's I think for the purposes of this class, this is the only thing. This is the only funny enough, this is the only determinant factor of whether we can solve the matrix or not. So here they're not going into the realm of eigenvalues. If you try to search this information online, they're gonna be like, oh well, are the eigenvalues this? Like, is your system stable? Blah blah blah. They start talking about things that have to do with controls. This right here, this just, if you have an equation in the form AX equals B, and they only give you the information of A, so what they're gonna give you, they can say like, oh, A it's equal to, and they're gonna give you like a 3 by 3. So you have to be, the whole idea of this question is, can you find the inverse of A? The only reason you can find the inverse of A, or the only reason you can solve the problem, is because the determinant has to be something other than 0. The determinant can be negative. The determinant can be positive. It just has to be anything that is not 0, just because of 1 over the determinant of A. And like, this is how you will solve. I think if you have a matrix like this, if you have A, B, C, D, something like this, I think you go D, A, negative B, and negative C, something like that, and 1 over the determinant of that if this was my matrix A.
You have to switch to BMC.
Oh, you have to switch to BMC? Okay.
Become negative. Well, wait a minute. Sorry about that.
No, but the A and D you swap, but the B and C become negative.
Oh, okay. Yeah. I haven't done I whatever you guys tell me, I will probably believe you because I do this with MATLAB or with Octave, or I don't do math by hand anymore. So but yeah, I think that's the case for a 2x2. A 3x3 is not like this. So you're gonna be given a 3x3 on the exam. So either know how to find the determinant of a 3x3 using your calculator, which I hope to God that that's what you're gonna be doing, and because that otherwise it's gonna take you a while. If you try to do the determinant of a 3x3, you have to like move everything to one, like you have to do some weird stuff. I forgot what it is. Of like you have to do, I think it's something like your A is gonna be on one side, and then on the other side you have like identity vector, and you have to move every identity matrix, and you have to like move everything from one side to the other. I don't know, some weird shit that you will see if you take matrix and linear algebra. But we have computers, we use computers, or in your case you can use a calculator. But what I was trying to say is just find the determinant, and the determinant will tell you the information that you need to know whether you can solve the system or not. I feel like this thing erases some. What?
What was the question you wrote? Because I can't read your handwriting.
Oh, I'm sorry. So they're gonna give you a system AX equals to B, and they're gonna give you they're gonna provide you the information of A. So A is gonna be a 3x3 matrix, and or it could be more. It could be a 4x4, 5x5. Ideally, I'm saying don't oversimplify it and go with a 2x2. So if you're given at a minimum a 3x3, they're gonna ask you, can you find the inverse of A? So can you find A inverse, and can you tell me whether the problem can be solved or not? And what this boils down is the determinant of the matrix A equal to 0 or not? If it's equal to 0, you cannot solve it. If it's not equal to 0, you can solve it. But remember, you always have to show your work, so know how to find the determinant of the matrix.
Wait, can you go over how do you find the determinant again?
For a 3x3, look it up online because it's a long process. That's why I'm suggesting that you use a calculator. For a 2x2, it's just 1 over the determinant of the matrix, and well, it's just like you swap these two guys and you make these guys negative on the corners. That's for like a 2x2. But oh, my cat is back. For a 3x3, it's completely different process. So just use the calculator. It's the best thing you can do. Just use the calculator, type it on the calculator, and tell it to find the determinant. That's the best thing that I can tell you. Otherwise, if you wanna send me a message, I can send you a link of where to find how to do a 3x3 by hand. It's gonna take you a lot of time, so it's not worth it to do it by hand.
And you said if it's equal to 0, then it cannot be solved.
Exactly, because you have 1 divided by the determinant and then the multiplication of the matrix. Like if this guy is 0, then it's undefined.
Makes sense.
Yeah, no problem. So let's find the inverse. So what I've shown so far, this is the first part of the exam. There's 2 more parts. I'm gonna try to step it up just because I see that we only have an hour left. So part 2, so that was part 1. Part 1 was all about direct methods. This one, it's gonna be iterative methods. So the second part of the exam is gonna be about iterative methods. So part 1 was direct method. Part 2 are gonna be iterative methods. And just as iterative methods go, again they're gonna say, okay, they're gonna start by saying consider the linear system. Consider the linear system. Linear system, it's in the form AX, and of course I already made a mistake because I'm thinking of one thing and I'm typing something else. Consider the linear system AX equals to B, and in this case what they're gonna ask you is if you can guarantee convergence. So can you guarantee that, God, I feel like my writing is getting wrong. Can you guarantee convergence? And remember, this is indirect iterative methods. Iterative methods are indirect methods, which means we're talking about Gauss Seidel. or Jacobi. So how do you guarantee that the system is gonna converge? If it's Gauss Seidel, how do you guarantee that my system will converge? Something that we talked shortly, like a little bit before, and the same thing applies in this case. So if I'm given an AX equals to B, and I want to absolutely guarantee that my system will converge, what do I have to test for? Correct, if it's diagonally dominant. So you have to make sure that you're gonna be given, because this is one of those, all of these problems are like you're given A and you're given B, and sometimes depending on what you're doing, sometimes you might be given X, but you're always given A and B, or sometimes you're only given A. Depends on the problem, but all of the problems begin with, hey, you're given a system in this form, here's the information, can you answer these questions? And so that's why it's very important that you have a good understanding of how like this goes, because you're gonna be given your A and B in this case, and if I tell you, hey, can you guarantee convergence? Yes, I can guarantee convergence because it's diagonally dominant. No, I could not. I cannot guarantee convergence because it is not diagonally dominant. So correct. So if you are given, I think I'm gonna go to the next page. If you are given the theoretical, there's something called a theoretical Gauss Seidel iterative matrix, and so let me tell you for a second. If I have something, or if I'm given something like, hey, you're given the theoretical Gauss Seidel iterative matrix. I have absolutely no clue what that is. I cannot remember it by now, but if they ask you something like, hey, you're given the theoretical Gauss Seidel matrix, and they're gonna give you a matrix that has like absolutely no meaning, at least for now. Maybe we'll have a meaning later on, but right now it doesn't have a meaning. So they're gonna tell you like, hey, you're given the theoretical matrix, you're given the theoretical, and I hope I'm writing this correctly. That's not it. You're given the theoretical matrix, and it just so happens that the matrix, when you have that theoretical matrix, you can use MATCAD, you can use MATLAB, or you can use anything to find the eigenvector. So you're given the theoretical matrix, and using that, I'm just gonna say, using that, we find the eigenvector. Or they're gonna say like, we found the eigenvalues. So they're gonna say, oh, we found the eigenvalues, and those eigenvalues could be something like this. Like they usually call that eigen of like whatever. So they're gonna say eigen, and they're gonna give you a vector, eigenvector. So an eigenvector, it's a vector composed of eigenvalues. And if you have a 3x3, your eigenvector is gonna be a size 3x3. And they can give you something like this. They can give you like, oh, this is 2.49 plus 0.7i, like for example, and then this one can also be negative, because you have one positive and one negative. This is gonna be, God, I'm getting PTSD from controls. This is like some root locus shit in here. But so you have to be able to look at this vector, for example, and extract some information from it. So what does a vector like this tell me? Will it tell me whether my problem will converge to a solution, whether it will converge to a solution, or whether it will not converge to a solution? And if I remember correctly, this comes from a part of stability. If I can recall correctly, I don't remember this 100%, but if you look at your notes, I think that is, if the magnitude of the vectors, if the magnitude of the real part of the vectors are all less than 1, I believe that guarantees convergence. I think for iterative process, like if you're doing Gauss Seidel and you find your Gauss Seidel theoretical matrix, and from that point you find the eigenvalues, I think I'm almost positive, because that's what I told you before. Like when we were looking at the matrix, and they're like, oh, how can you guarantee that this will find a solution? Like, how do you guarantee? And I say like, oh, this is jumping into like the realms of stability and controls. If I remember correctly, I think that as long as the real parts of my eigenvalues, like the real parts will be this, not the I, but this, and this. As long as those guys are less than 1 in magnitude, you will converge to a solution because your system is stable. Your system will not diverge. That is what I remember. However, take it with a grain of salt and go and read on the notes. Look in the notes and look for some more information, because that's what I think. But a lot of the stuff that I teach you guys is from memory. It's from memory, because I honestly, I don't have time to review notes before I do this kind of stuff. But
yeah, that's correct. That's what I've been reading with the note.
Okay, that's perfect. God, this guy's making me feel better. Every time I say something, I'm like, I don't remember this, and he's like, oh, you're right. I'm like, oh, I'm not full of shit. Yeah, I guess that's what happens through repetition every semester. But yeah, it's the eigenvector. So you're gonna be given those eigenvectors. You're gonna be given this eigenvector, which in return that means you're gonna be given the eigenvalue. So this question is gonna be all like tricky. It's not gonna be tricky. It's not gonna make sense. It's gonna be like, oh, we found this theoretical matrix, and then they give you the theoretical matrix, and you're like, whoa, what is this for? Like, it doesn't make any sense. And then they say, we found through that process, we found this eigenvector, and the eigenvector is going to have a bunch of eigenvalues, and they're going to say, okay, can you tell me if we expect a solution to a convergence to a solution or not? And it's if the real part of the eigenvalues is less than 1 in magnitude for all of them, we can expect the system to converge because the system is stable. So that's for that. And so in this problem in particular, we are this is kind of interesting, because they jump right away into the infinity norm of the residual is okay, yeah. So this is a I was gonna say non-direct. It's an approximated method. It's an iterative method. Iterative method of what? Of linear system of equation. Every time you see a question, and I'm just kind of like repeating myself from before. Every time you see a question that say, calculate the residual, you know that it's residual. It's equal to ax minus b. So in this case, this doesn't matter what they give you. Just the only thing you have to keep in mind is sometimes they will give you in the middle of the problem, like after they already gave you information and they ask you for some stuff, they're gonna be like, oh, by the way, I should write this in the correct notation. Oh, by the way, your initial get is gonna be 1 by 1, like for example. Then you know, oh, okay, if I want to calculate and then they ask you, okay, can you calculate the residual? Or like their favorite word is calculate the initial. Like there's something called initial. Initial means the 0 iteration, which means after you have even started solving the problem, because you don't need to solve a problem to start calculating residuals. You can do it right away, because you're given A, you're given B, and then they give you an approximation of like they give you your initial guess for X. So if they ask you for the initial residual is just your matrix A multiplied times your initial guess vector minus your vector B, and this will give you a vector with all your residual, and then you pass it through L infinity. You find the norm of that, and then you're gonna have just a value. This is just gonna be a scalar. So that's the process for finding a residual. So they're gonna ask you something like that, and then they are gonna say, okay, after that point, so you're given the information for your A, you are giving your information for your B, and you're given an initial guess. So that means that you are ready to iterate. So you're ready to do an iterative method. Ready to do some iterations, which means that from that point on, they will ask you to perform iterations using Gauss Seidel. And what kind of questions can you expect from Gauss Seidel? You can expect the same type of questions or the same kind of questions as on the first exam. Hey, after 2 iterations of the Gauss Seidel, what is your x vector? Like, what is your x vector, or what is the second component of your x vector? What is the first component of your x vector? So they will always tell you, like, oh, can you tell me x2 of 2? They will not use this notation, but they will say, like, this means the component number 2 after 2 iterations. So if you wanted to look at it graphically, here's component 1, component 2, component 3, and on the outside, here's the number of the iterations. So if after 2 iterations, they want this guy. And it could be something like this for residual, or it could be something like this for iterative convergence. That's pretty much what they're going to be doing. So they're going to say, like, hey, after carrying one step of the Gauss Seidel, can you tell me this component, like the second or the first component of your solution vector? After carrying 3 iterations, can you tell me the component number 3 of the solution vector? And same thing for the residual, same thing for the iterative convergence. So that's like 4 or 5 questions back to back. It's just, hey, can you calculate residual? Can you calculate iterative convergence? Can you calculate solutions at different iterations? And okay, so here's the question that we saw before. Can you calculate the number of floating point operations? And this is where floating point operations is what I was talking about before. So if I want to find the floating point operations, I will take n by n and multiply by k, the number of iterations that it takes me to arrive to a solution. And they will tell you your number of iterations. In this case, what am I doing? Give me 1 second. This is what happens when I have too many things on my... Okay, we talked about that. We talked about the theoretical. We went to 15, and then we're assisting. Okay. Given the Jacob... What? Why will they ask you the same thing? So they ask you the same question of the Gauss of the... So this question over here, this one that I gave you right here, this one, the information you have to keep in mind if you're talking about Gauss Seidel, or if you're talking about Jacobi. I'm tempted to say that they mean the same for both of them. However, it could be different. It could be different. I have not read about Jacobi in a very long time. So if you're given the eigenvalues, if you find the eigenvalues, they will ask you if you're expecting Jacobi iteration to converge, or if you're expecting Gauss Seidel to converge. And I am not sure which one is which. I know one of them has to do with eigenvalues, and I think the other one doesn't have to do with eigenvalues. But I that's one thing that you have to be just try to find that information, because I'm tempted to say this is the same thing for both of them. However, I could be wrong. And maybe one of them has to do with complex values and something like that. So just keep that in the back of your head. In the similar idea, like in the same way, you have to up here when I show you all of this, this is doing Gauss elimination. You can expect the exact same thing. So expect this with, which means, how many iterations till achieve, what is your solution vector after 2 iterations? What is the L infinity of your residual norm after 3 iterations? What is the component number 2 of your iterative convergence after 4 iterations? Something like that. So you can expect this with Gauss Seidel and with Jacobi. So you can expect this to be a thing with these two guys, with Gauss Seidel and with Jacobi. Yeah, and again, this guy will be relevant. They will give you, so K will be given when you have to find a floating point operation. So you have an n by n and then multiply by k, where k is given because k tells you the number of iterations that you are expecting.
So when they give you these like back-to-back questions, will they be multiple part questions, or will they just be like a string of questions?
everything is like multiple. Everything is like back-to-back questions. So what they're doing, it's like, let's say the next 5 questions, I give you information. I give you your A matrix, your B vector, and I can give you an initial guess or something like that. Or I can give you just your A and your B, tell you what type of system it is, like it's a linear system of equations, and I can say like, oh, and I can start just throwing questions at you. But those questions are gonna be based on the information that I gave you. So they're gonna give you, it's like a very, very traditional exam, like mathematics exam or physics or engineering exam. Like that's what I noticed. It's very like, you are given this information, answer the following like 6 questions or something, 4 questions or 6 questions. And if one of those questions is gonna require something more from you, they're gonna provide you that information. Like the one of these questions or one of these problems, you start with more of a conceptual type of thing, like, oh, like, will this converge, will this not converge, what information is this telling you? And then out of nowhere they're like, okay, here's your initial guess, start doing Gauss Seidel. So they're not gonna like tell you right off the bat what you're gonna be doing, but it's kind of like a build. It's like, oh, here's more information, here's more information, here's more information, depending on what you're doing. Like the information that you're missing will be provided to you. That's what I'm noticing from this type of exam. So just write down what you're given, write it down. Like if you get to a point and they're like, oh, you know, A is this and B is this, write it down, because you're gonna continue using that, and you don't want to go back to the beginning. But how are we doing so far? I haven't checked the chat. Let me check the chat just to make sure that I'm not missing. When is it as well? Blah blah blah. Blah 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 blah. Is that what you meant by plugging into a calculator the TI-36X Pro? Okay. I mean, I'll answer the question. If you guys have questions, I'll answer them in a second, because I only have half an hour. But do you guys have, any of you have any questions so far? Hopefully, you guys need to start like having a microphone, so I feel like I'm talking to the wall, except for like one guy who just keeps answering yes or no. But yeah, so that is like the biggest portion of the exam, I will say. The last questions, let's see, yeah. So the last questions of the exam will have to do with nonlinear Newton-Raphson, and this one I do want to spend a little bit time on. So nonlinear Newton-Raphson. And what happens with nonlinear Newton-Raphson, nonlinear Newton-Raphson can be confused with the system of linear equations, and that's something that you have to be very, 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 very careful, because every single semester there is somebody who just fucks it up, because they say like, oh, can you calculate the residual, and then go, oh yeah, residual, that's ax minus b. And it's like, no, that's not the residual. That's a residual for a linear system of equations. We're talking about non-linear system of equations, which is the reason why we have a whole different method called nonlinear Newton-Raphson, because we cannot solve it in the same way. So nonlinear Newton-Raphson, things that you want to keep in mind. And iterative convergence. So iterative convergence at whatever, let's say k plus 1. So if I wanted to find the iterative convergence at this current iteration, it's going to be equal to the absolute value of, and I should only use one because it's a vector, the absolute value of my k plus 1 solution, my vector, minus my vector k. So this one is very similar to the one before. They're all the same. The one that changes is the residual. So my residual vector at k, for example, this is going to be equal to the absolute value, and it's a vector, so that's why I'm only using one bar, is the absolute value of the function vector, because your function now, it's a vector. It's a vector, it's a combination of multiple functions. So my function evaluated at the solution vector at the k iteration. So it's the same idea as the project 1, as traditional Newton-Raphson, but now it's not, oh yeah, just take that value, take that x value, plug it into your function, take the absolute value of that. Now it's, yeah, take that vector, take that solution vector, that x vector, plug it into your function vector, and take the absolute value of that. And the solution of this is a vector. So your residual is a vector, and this one is also a vector. They're both vectors, which means, and I'm gonna keep saying this, which means we can do L2, we can do L infinity, and so forth. Which means we want to find norms. We want to find norms because we're dealing with vectors and we want to be dealing with values. So make sure you absolutely know how to find norms. That's very important. God, I feel like I'm running out of fuel. But yeah, this is very important. Epsilon, residual, they change, or perhaps residual changes for nonlinear Newton-Raphson. So what can I expect from nonlinear Newton-Raphson? So I'm gonna give like a quick introduction, just what it is. So nonlinear Newton-Raphson, you can expect multiple functions. So nonlinear Newton-Raphson, I can give you something like this. I can say, hey, your first function is an x and y, and I can give you something like, 2x plus 3y, and then you have a second function that is also in terms of two variables, and this one is let's say this is x squared plus y squared, for example. So this they will give you that, and then they will also give you an initial guess. So they can tell you something like this. They say x and y, because I have two variables, the 0, 1, the 0 iteration, so the initial guess, this could be something like 1, 1, just for the sake of simplicity. So this is all you will be given. And then things that you have to do, the way that you want to go about starting this problem, the first thing that you want to do is you want to find your Jacobian matrix. Your Jacobian matrix changes every single iteration. It changes every single iteration. Of course, maybe not in some cases, but you always want to find the general form of the Jacobian. So the general form of the Jacobian is given as, and this is how you find the Jacobian, you do the partial of the first function with respect to the first variable, in this case is x, and then the partial of the first function with respect to the second variable. Then you move to the next row. So columns represent changes in independent variables, so variable of interest, and rows represent the functions. So the second one is f2, so that's partial of the second function with respect to the first variable, and then partial of the second function with respect to y, with respect to my second variable. So in this case, if I was thinking just on this problem, then I'm going to take my first function respect to x, this is going to be 2. First function with respect to y, this is going to be 3. First function with respect to x, this is going to be 2x. First function with respect to y, this is going to be 2y, right? So this is my Jacobian. This is my Jacobian matrix. This guy never changes. So this keep. I'm gonna say keep it. Keep it at hand. Know where it is, because every time this guy will change because it depends on the values of x. The first Jacobian, my initial Jacobian, will have these two values. They will have the value of x plugging here, and it will have the value of y plugging here. At my second iteration, when I find new values of x and y, because I'm converging to a solution, I will plug those values in my x and in my y. That's why the Jacobian, if you remember from the previous project, there was something called, hey, evaluate your Jacobian. And every time you iterated, you just got this matrix of like, I don't know if it was 6 by 6 or something, or 5 by 5. You got it every single time, and you're thinking like, what the hell is this? Like, why do I keep getting this matrix and this matrix? Because it's required for you to have this matrix, because this is the process of like finding your Jacobian matrix. Because the reason you need your Jacobian is, number one, because they're gonna ask you about something. They can ask you like, hey, your Jacobian at the second iteration, can you give me value 2, like for example. And or in this case, like let me do the initial, because this is more realistic. So if I say, hey, your initial Jacobian, can you give me the value 2, that will be this one. I just have to plug the value of my initial guess in here, so the value will be 2. There you go. That's a question on the exam. But the reason we find the Jacobian is because when we're doing, when we're solving for 1 second. Okay, so when we're solving for a solution, if I want to solve for I'm gonna write it in terms of this equation, because I think this will make it easier for you to understand it. It's a 2 by 2. It's very simple. So if I want to find my next solution, so my x and y of my iteration k plus 1, which means my next solution, this will be equal to, and you're gonna see that it's very similar to normal Newton-Raphson or linear Newton-Raphson. So my next solution vector is equal to my previous solution vector minus the inverse of my Jacobian. So the inverse of my Jacobian, and you don't have to write all of this, I'm just writing it so hopefully it's easier to see it. The inverse of my Jacobian, let's see, 2x, oops, I think I made a mistake, so that's supposed to be, this is supposed to be f1. That's f2, and then this is, okay, and that's gonna be that's gonna be the inverse, but it's also gonna be at a certain k iteration, and this is gonna multiply my vector that is evaluating at x and y of the current iteration. So this is like, the notation is gonna get a little funky, but it's the evaluation of this vector. So I guess I can write it in this way, and I can say just at the k, and then the evaluation, that's for the first function, the second function at x and y at the k. So this is how you solve, this is how you find every single like iteration after. So this is why Jacobian is very important, because if I have the general form, if I'm finding, so I'm gonna find my first iteration. So my just so you can understand the example. So x and y at iteration number 1 is gonna be equal to my x and y at my initial guess. So because remember, this is k plus 1, this is k, then minus the inverse of my Jacobian, the evaluation of my Jacobian, that's right here at the first iteration. That will be plugging 1 1 in here. So I will have 2 3 2 times 1 and 2 times 1, and that will be the inverse of that. And then I want to multiply by the evaluation of the function at the 0 iteration, because this is supposed to be, all this case turned to 0 when this guy's 1. So this will be my first function evaluated at the initial guess. So I'm going to take this function, I'm going to plug a 1 here and a 1 for y. So this is going to be 2 plus 3, that's 5. So that will be 5 here. And I'm going to do the same thing with the second function. So I'm going to plug a 1 in here for this one and a 1 in here for this one, because that's my initial guess. So it will be 1 plus 1, that's 2. And that's what I'm going to put in here. And I'm going to go ahead and also replace this guy, my initial guess, because I know the value of it. So I know this is going to be 1 and 1. So this process will give me my value for x and for y at the first iteration. So that's why it's very important. If once I find this value, once I find the value of my first iteration, when I do my second iteration, I have to change these values. I have to change them. I have to change the x and the y for the corresponding values that I found after doing one iteration. So that's why it's very, all of this process, especially once we move into Gauss quadrature, all of this process becomes such a terrible housekeep. Like this is why we use computers, because computers are extremely good at doing one thing over and over and over again. They're extremely good at just keep doing the same thing. A very simple set of instructions, and just tell like, hey, can you do this 1,000 times? They will do it, not a problem. They will not make a mistake. People, on the other hand, we will fuck it up at like the second or third iteration. We can probably do one, get all cocky and be like, oh yeah, I got this shit, and then they do something stupid. Particular engineers. Engineers are known for being cocky pieces of shit. But this is how you do this nonlinear Newton-Raphson. If you have any questions with respect to that, I'll be happy to answer them. I want to spend the next 10 minutes just finishing up everything. So important that you know how to find the Jacobian element, because like I said before, I can ask you, hey, your Jacobian at your second element, at your second iteration, can you give me component 1, 2? And so component 1, 2 is this one, and they will want me to evaluate it, or in this case, it will be this one. And I will have to put in the x here. I will have to put the x of my second iteration, of my second, the second x solution that I found. So that's what that will be. And
Maria?
Yes.
Just to make sure, I know you just said it, I just want to clarify again. So pretty much what we do initially with that, the xy to the 0 iteration. So that would be basically computing with Jacobian, putting in the initial guess, and then getting that matrix of 2, 3, 2, 2. And then if it asks for like J naught 2, 2, you just go into the 2. But then if it asks for J 1, 2, 2, then we'd go for the process where you wrote right there of the x.
Yeah, exactly.
X, y, k plus 1,
Mm-hmm.
and that initial guess, and then we plug it back into the Jacobian.
Yeah, exactly. Because then at that point you will have to. So every time you're finding a new vector solution, you're also finding a Jacobian. Because you have to, like if I want to find my vector solution of the iteration 1, I need my vector solution of my initial guess, I need my Jacobian evaluated at the initial guess, and I need my vector of my functions evaluated at the initial guess. And if I'm finding the vector solution of my second iteration, then I need my solution of the first iteration minus the Jacobian evaluated at the first iteration, like the inverse of the Jacobian evaluated at the first iteration, and then multiply by the vector of my functions evaluated at the first iteration. That's why I say it's very important that you guys keep this at hand, because this Jacobian, this is the general Jacobian, this will not change. But when they ask you for a specific one, your variables will take the values of the iteration that they're asking for. So that's why every time you do an iteration, you will find a new solution for x and a new solution for y, and that will be a vector that will have an iteration attached to it. Like it will be your vector at the first iteration, second iteration, third iteration. So you can find the corresponding Jacobian by plugging that value, that solution vector, into your Jacobian. So it's kind of confusing. It's very confusing, and it takes some time to get used to it. That's why I'm telling you guys that it's very important that you guys go and do examples of this. I'm pretty sure Numerical Methods guy has a video on how to do it. I'll be surprised if he doesn't. I'm sure he does. But try one of those examples and be organized. Don't just write random shit everywhere and be like, oh, it's okay, I don't have to show it because I can do. Like, the worst people are the ones that they think they can do math in their head. Because the moment they make a mistake, they don't have no trail of their work. And so write down everything. Take everything one step at a time. It's like steps. It's like, that's why it works so well on computers. It's just steps. Go step 1. Write down what you're giving. You're giving your function, your f1 and your function f2. Write down your initial guess. So you're giving your functions, write them down because you will use them. Like you will, every single time that you have to find this vector down here, this vector evaluation of your function, you have to take these two equations and plug in the x and the y's that you need for the corresponding iteration. So keep this guy at hand. Your initial guess, you can do whatever you want, whether you can write it down and then show it up your ass, like whatever you want, but because you will only use it once. But your Jacobian, it's very important that you write it down, you create the general form, and keep that general form handy, because you will use it again. You will, every time you're gonna, these two guys, this and this, you're gonna keep going back to it every single iteration. So it's very important that you write it in a corner, you write it somewhere that it's very easy for you to come back to it. Usually what I do is I take like a red pen or something like that, and I put a star next to it, so that I have that visual feedback of when I'm flipping. If I have to flip the page and come back, I can quickly see the color. If you're colorblind, then you're fucked. Use a different color, but it's the same idea. And this is just the general equation. The general equation is the next iteration is equal to the solution of the previous iteration minus the Jacobian inverse evaluated at the previous iteration, and then multiplied by the vector of the functions evaluated at the previous iteration. This never changes. This is what you're going to be doing over and over and over again. But that's it. That's pretty much everything. It's like they're just going to ask you for the same thing they always ask you. Hey, can you tell me it's just like the quiz that we took for the last project. Can you tell me if they ask you the initial Jacobian is just take the Jacobian and plug in the initial values. That will be the initial Jacobian. So if I ask you for element 2 of the initial Jacobian, that's just plug a 1 in here and the answer is 2. That will be for the initial Jacobian. But they can also ask you for infinity norm of the residual after the initial residual. So after even no iteration, just plug in the initial vector into the functions, take the absolute value of that, and then do the L infinity. But then they can ask you like, hey, after 2 iterations, what is the element x sub 2? So this is why I want it to be. I think it's very important that you guys get used to notation rather than. Because if I can give you something like this. I can give you a function and I can say, hey, this is a function of x, y, and z. Kind of like how they do in calculus. Like, hey, this is a function of x, y, and z. This is the exact same thing as if I say, hey, this is a function of x1, x2, and x3. This is the exact same thing. This is the exact same thing. The only difference is here I'm trying to make you relate it to physics, or like, oh, this is a three-dimensional figure. I can plot in a three-dimensional graph. But I think it's very important for you guys to start thinking like mathematicians and stop thinking like physicists, because it's very, the limitations are, you're putting yourself limitations when you don't understand this notation, but you understand this one. Because on the exam, they're not gonna ask you, they're not gonna say, hey, at your second iteration, they're not going to say, at your second iteration, give me the value of y. They're not going to say that. They're going to say, at your second iteration, what is the value of your second element? Or what is the value of your first element? So your x is the vector at whatever k iteration. And all of the components inside of x are x1, x2, x3, all the way till xn. And this concept you can only represent it if you have a repeating set of like indices. If you have index, if you have coefficients, I cannot make an example like that using this guy. I can't, because then I will have to go through the whole alphabet, and I only have 21 letters, and then I have to go into the Greek alphabet, and it's just easier if you understand this notation. So be careful with that, because that's the notation that they will use on the exam. Yeah, just know how to find infinity norm after however many steps they ask you to do, like however many iterations. You remember, you can find infinity norm of the residual or of the iterative convergence. They never ask you for initial norm of the solution, because that will be dumb. There's no reason to find a norm of the solution vector. But yeah, they can ask you for a specific component. But that is everything that I have. So if you guys have any questions, go ahead.